Hello everyone, I want to use this video to provide more instructions for Lab 3, Water in Atmosphere. So in this lab, you will have, let me see, 1, 2, 3 questions, okay? And a lot of calculation, so stay with me, okay? The first question basically is to test your understanding on relative humidity. The key to answer this question is to use this formula. Okay, so as you know, as you learned in your textbook and our lecture meeting, well, the relative humidity equals to the actual water vapor content in the air divided by the water vapor capacity. So how much maximum amount of water vapor that can be held in the air. Okay, so this capacity is directly determined by temperature. So you're going to use table 1 to look it up if I give you certain temperature. This table is very important. You will use that in this question. You will also use that in the last question, question 3. Okay, so that is very important, this table. If you don't see the temperature listed here, you need to estimate, by the way. For example, if I give the temperature is, let's say, 12 degrees Celsius. Okay, so that number, you know that number should be between 7.6 and 10.6. Okay, so well, then because, you know, as you go, temperature go up, capacity will increase a lot. So I would guess it's between 7.6 and 10.9, 10.6. It's in the middle, but a little bit towards the higher temperature, right? So I will guess like 9, 9.5, 10 even. Okay, so that is how you estimate it. Okay, so here, based on this table, this number 1 sub-question in this bigger question, compare the warm air water vapor capacity. So the number towards this end compared to the number towards this end. Well, what do you see? How the temperature, how the maximum specific humidity or the maximum amount of water vapor that can be held in the air changes, okay, as temperature increases. Okay, so this is the question. And then, well, I want you to calculate if you increase the temperature of 1 kilogram of air. Remember, this capacity is every 1 kilogram of air. How many grams of water vapor that can be held in that air parcel? Okay, so I want you to calculate if you increase from 0 to 5. Okay, 0 to 5. What's the increase? Increase this capacity by how much? So keep in mind here, you need to calculate how much increased, not the, neither of those numbers. Okay, so how much increased? The same thing here for question 3 and 4. Okay, and based on your calculation in question 2, 3, and 4, what's your observation? Okay, you can see in those 3 questions, you increase the same amount of temperature, right? Okay, then, well, this increase every time they're same or not same. Okay, if not same, what's the trend? Okay, so you will need to answer that in this question. Okay, you will. What's your observation regarding to the changes? Okay, every time. So this is the thing I want to say. Okay, and well, then I want you to complete the table below to calculate the relative humidity. Okay, relative humidity. Remember, you need to use this formula. Okay, and here you can see 15, 25. You have your water vapor content, the actual water vapor content. Okay, and here you need to show your work based on the temperature, what's the max, okay, and say actual water content. Okay, copy this. Okay, so this is the actual. You need to use the table to look up the max, and then use a formula to calculate. Okay, give you a hint. Save it. Okay, alright, same thing for all these. Okay, and then based on your calculation in this table, okay, compare if the amount of water vapor in 1 kilogram of air stay constant, how will the cooling process, okay, influence its capacity? So basically, if you cool your air, can you increase your relative humidity or you decrease your relative humidity? Okay, so this is another observation you need to make. Okay, let me say this one, 1 kilogram, just cooling the air. Okay, keep it simple. All right. Okay, so the second question is to use sling cyclometer. Okay, on our study guide page, you see that very interesting video. I have another video to show you the same thing, how to use a sling cyclometer to measure relative humidity. The design of this device is actually very smart. Okay, they use two thermometers, okay, to measure the temperature of dry air and saturated air. Okay, so based on that video, understand how sling cyclometer works, and I want you to, based on those, the numbers I gave you. Imagine we have this sling cyclometer. We measure the air, dry bulb air temperature, wet bulb air temperature in those 4 scenarios. I want you to calculate wet bulb depression, relative humidity, and dew point temperature. Okay, and the table you will need is those 2 tables. Wet bulb, this one. Okay, this one is for relative humidity. Okay, and the one below is for dew point temperature. But the key you can see, excuse me, is to calculate the wet bulb depression. Basically, that is the temperature difference between your dry bulb temperature and your wet bulb temperature, and you calculate the depression recorded here. And based on that temperature, okay, for example, the first one I will get like 5, right? Okay, and the dry bulb temperature is 20, so you can see you need to use those 2 numbers. Dry bulb temperature is 20 here, okay? Depression is 5, so you look it up, okay? So the relative humidity of that scenario 1 should be 58. Okay, I give you the answer. So that is how you look it up. Okay, cross that here based on the dry bulb temperature and wet bulb depression. Remember that depression is not wet bulb temperature. Okay, same thing for your dew point temperature. Okay, those 2 tables actually is very here you can see that is the dew point temperature in scenario 1. Okay, so those 2 tables are very useful. We use that a lot. And once you finish calculation, take a look at your wet bulb depression. Okay, this line. Okay, so well, then think about this. When the air feels extremely humid, okay, if you have very humid air, okay, would you expect a larger or small wet bulb depression? Okay, explain your answer. Okay, to answer this question, especially to explain, you need to watch this video to understand how sling cyclometer works. Okay, so that is question number 2. Okay. Okay, question number 3, like I highlighted here, it's very important to keep in mind those information, but let me walk you through. Okay, so this question is about adiabatic cooling and warming processes, and to understand the rain shadow effect. It's a real-world scenario, real-world story. Okay, you will track the air parcel, which originates near the sea level at Eureka, California. It's a town by the ocean in Northern California. Okay, and the wind from our ocean will blow this air up. Okay, you can see wind is here, will blow this air up to climb our coastal ranges. 2,400 meters at the crest, at the top. Okay, so as you know, once the air parcel is forced up, it will get cooled, right? Because number one, you have lower and lower air temperature. You will also have lower and lower air pressure. And when you reduce the air pressure, your air parcel will blow up. And when they blow up, this adiabatic cooling process, right? The temperature will decrease. And then on the other side, okay, we call that leeward side. This side we call the windward side. Leeward side as the air parcel decrease their elevation, descending, you will see the temperature warm up. One thing is the surrounding air become warmer, and you also have higher and higher pressure, right? Your air parcel will be squeezed, and the temperature will be increased. Adiabatic warming process. Okay, so very important. Okay, how fast the temperature change as it go up or go down. Okay, so if your air is not saturated, you use DALR to calculate the temperature change. Okay, and if the air is saturated, you will need to calculate, use MALR. Okay, so that is very important. Okay, and let's assume the sea level, the air parcel, when it started, that air temperature of the air parcel at Eureka is 18. Okay, dew point temperature at Eureka is 12. Same thing. Okay, here 12, not same thing. It's the same air, but the dew point temperature is lower. That is the temperature when you see the air get saturated. Okay, and you have, well, at the beginning it's not saturated. Okay, it's not saturated, so you need to determine which lapse rate you need to use. Okay, and to calculate the temperature decreases as the air parcel go up, right? Okay, and the dew point temperature can be determined by the formula. Okay, I need to change this one. Okay, and in which this TD is dew point temperature, Tair is air parcel temperature. Okay, RH is relative humidity. Okay, so you are going to answer those questions. One thing is very important: follow the order. You cannot skip. You cannot skip, guys. You cannot skip. Okay, follow the order to calculate humidity, to calculate the maximum water vapor that can be held once it first gets started at sea level. Okay, you need to follow the order and use my hint here to think. Okay, you can discuss with your lab group mates. Okay, for this lab, you're also welcome to email me if you have any questions. Okay, so we will do the calculation at 3 places. When one is, in this ascending process, rising process. Second one is at the top. Okay, the third one is at the red bluff. Okay, so read the question carefully, and also use a hint. Very important. Okay, all right. So this is this lab. Let me know if you have any questions. Okay, I will see you in the class. All right, bye for now.